Okay guys, today we're going to solve related rates problems, and with this there is a process to it, and this is the process that you want to follow. Now you don't have to follow all of them in order, but you do want to try to do these, and this is a template for solving related rates problems. Much like optimization problems, related rates problems, now we're going to introduce implicit differentiation. When you are differentiating with respect to a variable that's not in the problem, you have to attach a d variable. So we're going to be differentiating with respect to time. So we're going to have to attach a d dt. That is the rate of change with respect to time. So this is the process. You may want to press pause now to write this process down. So here's our first example, a sliding ladder problem. And this example has got a lot of things going on with it. First of all, understanding the problem. We have a 13-foot ladder that is leaning against the side of a house. The base is sliding away. When the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. And then what the problem asks us to do is in 3 steps here. So first of all, what I want to do is read those steps and decide what my picture should look like. This is a classic right triangle problem. This is my picture, and you'll notice that the ladder is leaning against the house. These should be straight lines here, but the picture is just to help me out. So I'll move on from here. Now I have to assign variables. I'm going to assign variables, very generic variables. My variables are assigned. I'm going to let x be the distance that the bottom of the ladder is from the house. Z is going to be the length of the ladder. Y is going to be the length from the top of the ladder to the ground. And theta is going to be the angle that is between the ladder and the ground. So I have these variables established for me. Now I'm going to go ahead and list them. Variables that I have. I have 4 different variables. These are my 4 different variables. I'm going to go ahead and list each variable's rate of change with respect to time. So that would be dx dt, dy dt, dz dt, and also d theta dt. So now I have these variables and their rates of change. I know that the length of the ladder Z is 13 feet. Since the ladder is 13 feet, it's a constant. So the change or the rate of change of the ladder with respect to time is going to be 0. The derivative of a constant is 0. The ladder's not changing its length at any time. I also know that the length between the bottom of the ladder and the house is 12 feet, and that's in particular what I want to, the time in which that I am evaluating rates. I know that the ladder is moving away from the house at 5 feet per second. I can find out the value of y just by doing the Pythagorean theorem. So using the Pythagorean theorem, you would have that x squared plus y squared equals z squared. So then y has to be thus y has to be equals to 5. At this particular time, y is equals to 5. So the first question, question A, asks us how fast is the top of the ladder sliding down the wall when this is the case, when it's 12 feet from the wall. So I am seeking, or I am trying to find dy dt. Now I can relate my variables using the Pythagorean theorem formula. X squared plus y squared equals z squared. This is my formula to relate the three side lengths. X squared plus y squared equals z squared. Now I'm going to differentiate both sides with respect to time t. When you do that, you have to attach a d variable dt. This is the result. Notice each term has a factor of 2. So you can go ahead and divide each side by 2, and that's going to get rid of all 3 of your 2's. From this point, I am searching for dy dt. I know all of the other variables. I know x. I know dx dt. I know y. I am seeking dy dt. So I want to isolate the dy dt. I also know z, and I know dz dt. From here, you're just solving for this particular variable. Just treat it like an x, and it's just solving a linear equation. Just treat it as this is the variable that you need to solve for. So I can substitute in for my other variables, x, dx dt, y, z, and dz dt. This is the resulting equation. The length of the base from the house is 12. It's moving at 5 feet per second. And since it's increasing distance, or the distance that the base is getting away from the house, that rate is a positive rate. I know that my y variable is 5. I solved that because the length of the ladder, the length from the base to the house, I used the Pythagorean theorem. I'm searching dy dt equals the length of the ladder z is 13, and the rate of change in the ladder is 0. So this will simplify. This is the resulting equation. Subtract 60, divide by 5, and you'll find dy dt. So I have that dy dt equals -12. Now thinking about units, the units are going to be in feet per second, and the sign of the rate is negative. That means that we are closing distance, or the distance is getting shorter. That means that the rate should be negative. So this is going to be -12 feet per second. And that is the solution for part A of this first problem. Now for part B. Part B, we can use the same values that we had, the same variables that we had, because it's asking for the rate of change of the area between the ladder, the wall, and the ground. So we need a different formula to relate these variables though. The area of a triangle is 1/2 base times height. So that is going to be the formula that we use to solve this problem. So I'll get everything set back up, and then we'll use the fact that the area of a triangle is 1/2 base times height to find how fast, or the rate of change of the triangle formed by the ladder, the wall, and the ground. So here we are. We have that the area of this triangle is 1/2 times x times y, and we have to differentiate both sides with respect to t. So on the left hand side, the derivative of a with respect to t is just 1 dA dt. And then following the formula using the product rule on the right hand side, this is what you end up with. Using the product rule, the left-hand side derivative of a is 1, but you have to attach a dA dt because that's what you're differentiating with respect to is t. The right-hand side, using the product rule, you have the derivative of the first is derivative of 1/2 x is 1/2 times the second, but then you have to attach a dx dt, plus leave the first alone, leave 1/2 x alone, derivative of y is 1, but you have to attach a dy dt because that is the variable that you're differentiating with respect to. So clearing this up, here is what I have. This is my formula. And I have all of my variables that I need. I am seeking dA dt, the rate that the triangle, the area of the triangle is changing. So I have all my other variables. I have y, I have dx dt, I have x, I have dy dt. I can plug in and solve for dA dt. Now it's just computations. So that gives me my right-hand side is 1/2 5 times 5 plus 1/2 12 times -12. That's going to give me the rate of change of the area of the triangle. Now, if I'm just looking at this, it looks like I'm going to end up with a negative value. Now, does that make sense? It should make sense to you that the rate of change of the area is negative. The area is decreasing. Okay, that's a little check that you can do. And what happens whenever you perform these computations is you come out with a value. Now, dA dt is going to be in terms of feet squared per second. So you get negative 59.5 feet squared per second. Okay, this is a classic problem with related rates, a conical tank. So you have a conical tank that's point down. So this is a conical tank that's point down. It has height 10 feet, base radius 5 feet. We have water running into the tank at 9 feet cubed per minute. So we have a lot of stuff going on here. But this is a classic problem, and these problems are related. Anytime you have cone problems, they're related by similar triangles. So from this picture, I have two different triangles that I'm looking at, and I'll show them more clearly. Okay, so we have that the cone is 10 feet high, base radius of 5, and then we have our variables, the height of the water and the radius of the water. So no information is given about the radius of the water. So let's go ahead and eliminate that variable, and we can relate these with similar triangles. So we have 10, the height of the cone is to the height of the water, as the radius of the cone is to the radius of the water. And we can go ahead and eliminate the variable r. So cross multiply. Divide by 10. And you get that the radius of the water is 1/2 the height. So now, using our volume formula for a cone, volume is 1/3 pi r square h. But r is 1/2 h. So you can substitute that in there, and we will be in terms of just h. So simplified volume equals 1/12 pi h to the 3rd power. Now differentiate both sides with respect to t, and then plug in the values that you know. So when you differentiate, with respect to t. When you differentiate both sides with respect to t, this is what you end with. Now plug in what you know. You know dv dt. That's the rate at which the volume is changing with respect to time. So that value is 9. You know h. It tells you we want to know when the water is 6 feet deep. And then we solve for dh dt. So we have 9 equals 25 pi over 4 times dh dt. Divide both sides by 25 pi over 4, and you will solve for dh dt. So you get that dh dt is 0.458, and in context of this problem, that means that the height is increasing about almost a half a foot per minute at this particular moment in time. Again, this is a classic cone problem. All you need to do is just relate your variables with similar triangles. Anytime you have cone problems, that's the general format that you want to do. Okay, reading this problem and understanding it, you have a balloon rising vertically and a bicycle that is going underneath of the balloon. So it sounds to me like this is going to be a right triangle problem. The balloon is rising vertically. The bicycle is going underneath of the balloon. And they relate these with the distance between the two. That would be the hypotenuse of the right triangle. And then they ask a question. They ask about 3 seconds later. Well, the balloon is traveling at 1 foot per second. When the balloon is 65 feet above the ground, that's when the bicycle is directly underneath of it. So we want 3 seconds later. So if it's 65 feet above, then 3 seconds later would be 68 feet. The bicycle, if it's traveling at 17 feet per second, 3 seconds later it's going to be 3 times 17, 51 feet past the balloon. So relating these three, they relate with a Pythagorean theorem, distances. So I'm going to label my distance that the balloon is above the ground as y. I'm going to label the balloon above the ground as y, the bicycle as x, and the distance between the two as z. My formula that I'm going to use is the Pythagorean Theorem. X squared plus y squared equals z squared. I know x would be 51. I know y would be 68. I know dx dt. I know dy dt. I am seeking dz dt. I need to find z. You can find that by using the Pythagorean theorem. 51 squared plus 68 squared, and then take the square root of that. And that comes out very nicely to 85. So now differentiate both sides with respect to t. Since they all have a factor of 2, you can cancel that out, or you can divide both sides by 2. All of the 2's will cancel. And now plug in, and you can solve for dz dt. So after you do the math and you solve, you get that dz dt equals 11. And that is going to be in feet per second.